And with that, let me introduce you to today's speaker. It's James Vose, who's with USDA Forest Service Southern Research Station and out of the Center for Integrated Forest Science, and is located here at North Carolina State University in Raleigh, North Carolina. And with that, I'll turn it over to Jim.
All right. Thank you very much. I assume everybody can hear me okay. If not, let us know and we'll adjust accordingly. I appreciate the opportunity to speak with you by webinar today about a really important topic, and that is the relationships between forest and water. This is one of 3 kind of consecutive webinars that are meant to be connected together. In about a month, there'll be another one that talks about land use and landscape level processes and how those influence water resources, and then in about a month after that, one on best management practices. And this first webinar was an attempt to provide a bit of a precursor to those following ones. So I encourage you to stay tuned for the next couple that will be coming about a month out and then another month out. So I'd like to do 3 things today. I'd like to first review some basic forest hydrology principles and focus on the ones that really relate to the supply of high quality water. With that, I'd like to identify key watershed features that regulate important processes, and then discuss how management affects water yield and water quality. And for the management, I'll primarily focus on forest cutting and prescribed fire. Now, this presentation is going to span the spectrum from very basic knowledge that you may have learned or either in school way back when or through on-the-job training, but also I'm going to blend in some research and some highly technical information. So for some of you, it may be a refresher of some things that you already know, and others it will be new information that you perhaps have never heard before. But I think all in all, and I hope all in all, you'll learn something in the process. Now, this is a slide that just shows sort of a historical trend in global water withdrawals and then future projections. And the future projections have a wide scatter about them because it depends on population growth estimates and conservation practices. But the bottom line is fresh water is a critical resource that's destined to become even more critical in the coming decades. Now, it used to be that in many parts of this country in particular, there were areas where fresh water was so abundant that most of the efforts were focused on trying to control flooding, and the notion that water resources would become scarce was further from most people's minds. In many regions now, that's no longer true. This headline was from the Charlotte Observer in North Carolina, and this is a city, town of Statesville that came within a few days of running out of water. And the reason that happened is that the last few decades have been subject to some serious droughts, but also, as the panel on the right shows, this is a region of very fast population growth, with the average person using about 100 to 200 gallons of water per day, industrial and agricultural growth to support that growing population. This is a headline that's likely to be played out and has played out since this headline time and time again. Now, the reason that we're talking about forests and water is that forests have a very important role to play in supplying water to aquatic ecosystems and people. We know the following 2 statements. One is that the cleanest and most regulated supplies of water come from forested landscapes. We also know that forests can be managed in ways that do not negatively impact water resources. And this has been concluded to be settled science by a fairly recent National Research Council report. And I will say that there's very few things in natural sciences or natural systems that we have this much confidence in. But this is one that those 2 statements are recognized to be true. And it's a good thing that we know about that, and a good thing that we know the value of forests for supplying water, because about 60% of the nation's drinking water supply originates from forests. Now, how do we know this? Well, one of the reasons that we know this, and one of the reasons that it is settled science, is this is an area that we literally have decades of scientific information on. The original origins of the U.S. Forest Service in particular had a lot to do with the fact that land managers and the state of the science at the time recognized that there needed to be more information about the relationship between forests and flooding in particular, but also forest management and water quantity and water quality. As a result, there were several experimental forest watersheds set up across the United States, and those experimental forests and watersheds have provided a tremendous amount of information, a tremendous amount of sound science on the relationships between forest and water. The graphic that you see on this slide is where I spent the first 25 years of my career, and where I developed a lot of the information that I'll be presenting today. So I will primarily be using results from studies that on or around the Coweta Hydrologic Lab, or certainly in the southern region. But the principles that I'll talk about will be generally applicable across the entire United States, and certainly in the eastern United States. So let's just start with the simplest notion, and that is, what's a watershed? And quite simply, a watershed is a unit of land that receives, modifies, stores, and distributes precipitation. They can be small, they can be large, ranging from the small, say, 50-acre watershed that you see in the black and white photo on the left, to a 6,000-acre basin on the color photo to the right, to large river basins in the state of North Carolina on the upper right. Now, the easiest thing to understand, and where most of the studies have occurred, are in these small headwater watersheds. And part of the reason is because you can control many of the complexities. Soils are essentially the same, vegetation the same, aspect, etc. As you move from that small headwater scale watershed to larger and larger scales and up to landscapes, it becomes incredibly complex. And instead of the watershed being comprised of one land cover type, it now becomes a watershed comprised of urban, suburban, agriculture, forests in a diverse and interconnected matrix. And I encourage you to join the webinar in a month or so, which talks about the implications of some of those complexities at those larger landscape scales. What I'm going to focus on primarily today, however, is the scale in the lower left-hand corner, essentially the small watershed comprised primarily of forest cover. So what are the attributes that make forested watersheds so valuable for supplying clean water? And what I want to do is just kind of review in a general way what these key attributes are, and then tie those into how those might be changed or manipulated by management activities. Well, in its simplest form, this is a watershed diagram. This is a large example of a large watershed where we have the inputs and precipitation, outputs and transpiration. What's left over ends up going into the streams or going into the groundwater for groundwater recharge. But what I really want to focus on is sort of the internal processes that go on within a watershed that ultimately regulate the quantity and quality of water. Same kind of model as before, in that we've got precipitation inputs and evapotranspiration outputs. But how that residual water, or how that water that's left over after there's an evapotranspiration loss, moves across the watershed is a strong regulator of both water quality, but also the quantity and timing of stream flow. What flows across the surface is important for delivering sediment to the stream, and also has a strong impact on storm flow patterns. What flows beneath the surface is important for delivering nutrients, and also has a important role in generating base flow and mitigating some of those extremes that might occur from high intensity storms. Also note on this graph that I have distinguished the upland forest from the riparian, because the riparian area has a very critical role in moderating especially water quality, but to some extent water quantity. And I'll discuss all of these attributes at some point here in the presentation. So I'm going to really just focus in on the attributes that are in this box. I'm going to talk primarily about vegetation, soil-water interactions, how those are influenced by evapotranspiration, overland flow, and storage and filtering. Although the type and distribution of precipitation and snowfall is important, I'm not going to focus on that much here in the presentation, and I'm not going to focus much on the outputs in terms of things like storm flow or groundwater recharge. I'm primarily going to focus on those key watershed processes that determine water quantity and water quality. So ultimately, what determines how much water comes off in either surface runoff or how much comes off in terms of being able to recharge deep groundwater is determined by the balance of the forest water balance. And that is essentially, in its simplest form, the difference between how much comes in precipitation and how much is lost in evapotranspiration. Evapotranspiration is comprised of two components: transpiration, how much is taken up by the trees and lost through the stomata, and interception evaporation. Now this can be this evapotranspiration component can be a tremendous amount of the water budget. In areas where stream flow is really low and variable, and in some cases have very little base flow or perennial flow, usually that's a situation where evapotranspiration and precipitation are essentially equal, or in some cases potential evapotranspiration is even greater than precipitation. So let's first talk about interception. A raindrop very rarely makes it directly to the forest floor on a forested watershed. A portion of that rainfall actually never reaches the forest floor, and it's evaporated back into the atmosphere. In hardwood forests, that value ranges from about 10 to 15%. In conifers, it ranges from about 15 to 25%. Now, this is an interesting phenomena, and a lot of people don't realize it, that up to 25% of the rainfall that falls on a forested watershed never actually makes it to the ground. It's intercepted and evaporated back into the atmosphere. And that higher number occurs when you have annual rainfall where you have a lot of light rain, or whether there's a significant amount of leaf area or branches that intercept and provide that surface to evaporate back out. So most of what actually reaches the forest floor is through fall and stem flow, and that's anywhere between 90 to 75% of what comes in precipitation. What then does come through fall and stem flow moves through the forest floor through the process of infiltration. And you can see from these figures what really distinguishes a forested watershed from most other land uses is two things. One is, in some ecosystems, a fairly dense understory vegetation, which is shown in the lower graph, which adds another barrier and another place where you can get some interception and evaporation, but also a very thick forest layer, litter layer, and humus layer. So again, very rarely does a raindrop that comes through an infiltration directly hit the soil particle. It has to pass through another round of vegetation in the understory or through the thick layer, litter and humus layer. Now there's lots of things that determine infiltration rate. Some of them are physical, and essentially uncontrolled by forest management activities, and that would be things like soil texture. There's not much that can be done about soil texture. You either have a sandy soil or a clay soil or silt loam soil. But there are other things that are more biological in nature and can be impacted by forest management activities, such as the thickness of the litter layer, the amount of soil organic matter, and the level of compaction. The kinds of conditions that promote a rapid infiltration rate would be a thick litter layer, of coarse textured soil like sandy soil, high soil organic matter, unsaturated antecedent conditions, and low compaction. And the kinds of things that would precipitate low infiltration rate would be a thin layer, clay soils, low soil organic matter, saturated soils such as after a heavy rain, or in areas that have a high water table, or areas that have been highly compacted. And you can begin to see that if you do have a situation where you have a very clay soil, characteristics that you can control, like a thick litter layer or high soil organic matter, or reducing compaction, could be important for offsetting that low infiltration rate. For the most part, overland flow, or Hortonian flow as it's called, doesn't happen very often in many forests, because the infiltration rates are really high, or certainly high enough that water rarely flows along the soil surface. Now, there are exceptions to this, and there are certainly times where rainfall intensities are so high that water, and especially if it's a long, high-intensity storm, that all the pores in the soil get filled up and water can flow along the surface. But it also can happen in heavily disturbed or heavily compacted areas as well. And these graphs kind of show some of the worst case scenarios. Down the lower is some historically bad land uses in the southern United States that have very high erosion rates, very low infiltration rates. And then the upper right corner is a classic example of an abandoned legacy road, where that long-term compaction essentially allows water to flow right down the middle in sort of a mini stream. And then the lower right-hand corner is to discuss a little bit about what might be to come in terms of infiltration rates. Is that if there is a continuation of increased frequency of severe storms and high intensity rainfall events with climate change, the notion of overland flow and erosion and sedimentation that may come with that may become an increasingly important factor for land managers to deal with. So, first question, just to get a little bit of participation by the audience here. There is not an A, B, C, or D answer here. This is one where I'll give the answer in the next slide. But the first question to think about is based on what you know and what I've told you so far, what are the most vulnerable areas in a forest watershed for overland flow, erosion, and sediment delivery to streams? Think about that for a minute, and then I'll click on the next slide.
Okay, and Jim, if people would like to answer in their chat box too, they're more than welcome to use that to begin some discussion on the answers and any questions that you've had to date. Okay, thank you. Well, I kind of gave away the answer, but one of the early questions at Coweta is, in a lot of experimental forests, is what causes erosion in combination with forest cutting. And many believe that it was the mere act of cutting the forest themselves was a cause of erosion. And what the science has shown, that the real critical areas for erosion and sedimentation are the roads and the stream crossing in watersheds. And so best management practices that protect or disconnect the road from the stream through proper sizing and location of culverts, proper and complete brush and vegetation barriers, things like sediment traps, broad-based dips, and close attention to stream crossings are really critical for disconnecting the road from the stream. Again, you'll learn more about this if you tune in again, I think in the third webinar on best management practices and water quality. Another and large component of the water budget is transpiration. So we talked about interception. Water drips down through the forest canopy and stems, infiltrates into the soil. Now, some of that water then, in some cases a large amount of that water, is going to be used by the trees. Now, transpiration rates can be a very large part of the water budget, sometimes up to 80%, in some environments 100% of the water budget. So this is a big part of the water budget, which can be manipulated either intentionally or unintentionally by management choices. The rates vary among species, vary among time of year, climate, and tree age. And this is driven by the gradient, by energy,
and the gradient between the moisture in the air and the inside of the leaf through the stomata. The graph on the right-hand side are actually some pretty rare data. With the advent of some technology, scientific measurement technology called SAPflow, scientists are now beginning to be able to individually estimate how much water certain tree species use. On the right-hand side, you see the color codes of a bunch of different species. If you remember some of your Latin names of your trees, you'll recognize these or might be able to guess them. But I'll just run through them. There's Betula lenta or birch, Nyssa sylvatica, black gum, Cornus florida dogwood, Liriodendron tulipifera is yellow poplar, Acer rubrum is red maple. Looks like there's a Platanus occidentalis, which is I think a sycamore. There's a hickory, Caria species, a Quercus prinus, a chestnut oak, Quercus rubra, red oak, hemlock, Suda canadensis, and white pine, Pinus strobus. What you'll notice is let's just say at 30 inches of diameter, which is about a 12-inch tree, the range and the amount of water used by these various species varies from about 10 kilograms per day to 100 kilograms per day. So huge variation in the amount of water that individual species uses. And that has a lot to do with its morphology, physiology, xylem anatomy. A 12-inch tree, just to put it in units that might be more familiar with you, a 12-inch tree in using these data is using up to about 30 gallons of water per day. So you can see that depending upon the successional stage, which might favor one species over another, or management choices which favor one species over another, there can be a very large difference in the amount of water that's transpired by the particular species in the forested watershed. And this then begins to translate into forest types, which are comprised of predominant species types. So the amount of forest transpiration varies by forest type and is influenced by the climate and soils where they grow. In this case, the box on the right-hand side there shows a range of about 244 millimeters per year of transpiration longleaf pine savanna, upwards to about 900 millimeters per year in transpiration in a loblolly alpine coastal plain forest sitting in essentially a bathtub of water. So very large differences in the amount of water that is used by these different forest types. And if you use that water balance, that precipitation minus evapotranspiration, the result would be very large differences in the amount of stream flow coming out of these forest types, or large differences in the amount of groundwater recharge capable from these forest types. Now the water that's not used by transpiration then is essentially either evaporated out through the forest floor. That is a very low amount in most forests because the forest cover and thick forest litter layer minimizes soil evaporation. But what is a really important process in forests is the soil water storage component. And the analogy is that the forest soils act like a sponge, holding on to the soil water and slowly releasing it to groundwater recharge in streams. And this process is really what's going on in these two graphs that I show here. These are two side-by-side watersheds receiving essentially the same amount or the same pattern of precipitation. The one on the left with the title of forest is a forested watershed. Precipitation are the black bars. Discharge or stream flow is the gray line with the very small bars. On the right side is the same units, precipitation in the black bars, discharge in the gray bars. And you can see a very large difference in both the amount of water that's coming out of the watersheds and, more importantly, the pattern. The one on the right side has much higher flows, but a very spiky pattern that almost mimics the precipitation inputs. And that's due to the fact that the large impervious surface results primarily in overland flow and not that slow water release that comes from that forest soil acting like a sponge. Now, a lot of folks have thought, well, isn't this good? that all this extra water is coming out of this urban area? Wouldn't that be a way to solve water supply problems, because there isn't that water use by the trees? Well, a couple of things happen. One is most of this water can't be captured. It's flowing so fast that it flows right through water treatment facilities, or flows right over or right through storage reservoirs, and it doesn't recharge groundwater. The second thing that happens is that in addition to this water being so fast and delivered in flashes or pulses that it can't be used, it almost always has a much lower water quality as well. So any gain that might be achieved for the extra quantity is offset by the reduction in water quality. Okay. So what I'd like to do now is just hone in on one of the key zones in a watershed, and that's the riparian zone. And that riparian zone is a critical interface between that upland component of the watershed and the stream. Now, you have a riparian zone whether you're in a flat area without a lot of topography, or whether you're in a very steep mountain watershed. All watersheds have a riparian zone in that near stream area. And of course, the riparian zone has some key functions. Most of you know the sediment nutrient filtering, stream bank stabilization, wildlife habitat and corridors, wood and organic matter supply, stream temperature, biodiversity. The primary function, though, that I'm going to talk about is the first one, and that's the sediment and nutrient filtering function. And so as that water moves down through gravitational forces down from the upland down into the riparian zone, there's really two areas of interaction. One is in that hypereoric zone, which is the subsurface interaction, where primarily nutrients are exchanged back and forth. That's the one that's in the dashed circle there. And then the other area of interaction is what flows down through lateral flow down through the unsaturated, or in some cases saturated soil from the upland. And that, of course, is also exchanging nutrients and water. And then if there is going to be any overland flow, it typically might occur in that riparian zone, where it's more likely that the soil will be saturated. So there may be some overland flow, especially during high storm events in that riparian area as well. Now, in that riparian zone, there are some key processes that occur that are really important in their role for maintaining the ability to filter both sediments and nutrients. The first and foremost is the riparian zone, for it to be functioning effectively, needs to have vegetation. And that vegetation can be and is typically both above ground, woody or trees, but also the shrubs and the herbs in that riparian zone are really important for trapping and cycling nutrients that may be flowing through the subsurface. The litter layer and the wood are very important for filtering any of the sediment that flows down, if it does flow down in overland flow. And having a good coarse woody debris layer in that riparian zone is critical. The other thing that's important is microbial activity. In riparian zones that are frequently wet and in some cases saturated, the microbial activity is really important for either immobilizing nutrients in their normal biological processes, or for nitrogen in particular, the process of denitrification is actually a way where organic nitrogen and inorganic nitrogen that would flow into the stream would be converted from that elemental phase in the soil solution to a gaseous output, which is shown on the right side bubble coming out from the microbe. So very critical functions, some of which are unique to the riparian zone, especially the microbial processing, and doesn't occur in the upland. So there are some, and continue to be, some real critical issues related to riparian zones. And one of the most important questions that's asked is what is the proper riparian zone width in a forested watershed? And that can be defined in a variety of ways, but one of the ways it can be defined is what are the critical functions that occur within whatever that width is from the stream edge towards the upland system. And I'm going to talk about that a little bit here in the following slides. The other questions that are really important and will be talked about in the best management practice webinar, a couple of webinars now, is how wide should the riparian be to mitigate upland disturbances, and how much of the riparian zone can be disturbed and still provide critical function. All of these are have a fair amount of science behind them, but still uncertain in some places. Now, one of the things I'd like to share with you is an actual study that we did in the mountains of western North Carolina to try and understand exactly how wide a riparian zone is in terms of critical function. And these are the types of functions that I showed you in the previous slide, the things that are important for filtering nutrients and sediments. So how much vegetation is there and what kind is it? How much litter fall or litter layer and forest floor is there? How much coarse wood is there? What's the soil moisture and temperature factors that regulate nutrient cycling processes? What are the amount of soil nutrients? And how does soil nutrient cycling change? And these are the kinds of studies that need to be done to characterize the width of a riparian zone in a functional way. And essentially what we did is measured these parameters at fixed intervals from stream edge all the way up into the upland forest, and then looked for where those key parameters changed, with the assumption that where they changed was a reflection of a different functional state or a transition from riparian to upland forest. Now, I'm not going to go into the nitty-gritties of the statistics or exactly how we did it. Those data are here, and I can send you a paper. You can look up a paper by Barry Clinton in Canadian Journal of Forest Research in 2010. But basically what we found is that there was a noticeable transition, a statistically significant transition in a whole lot of these parameters. And most of them converged around 30 feet. Now it turns out that the typical riparian zone width in the mountain region, or the minimum width, it was about 30 feet. That was determined basically by experience and to some extent by vegetation characteristics, but it was confirmed and shown that it was about a 30-foot riparian width. So at that area, those parameters, forest floor characteristics, litter fall, woody debris, and below ground soil environmental and nutrient characteristics essentially changed. So that 30-foot was the functional width. Okay, and again, more will be talked about the riparian zone, best management practices, and functional width from a standpoint of protecting from disturbance and what kind of management activities can be done in them in a further webinar. What I'd like to do now then is transition into the discussion of sort of an intact forest to what happens when the forest is either cut or burned. And this is then titled The Effects of Forest Management on Water Yield. So I'm going to start with just sort of 3 statements about what we know. And what we know is that stream flow increases after cutting are proportional to the amount of forest that's cut. How that responds and how long it responds depends on what vegetation regrows or what is planted behind it, and that the responses are dynamic, and that the earliest responses right after cutting diminish as the forest regrows. And we know this from long-term, and I mean 60, 70-year-old studies, so decades of research from paired watershed studies, not only in the South, which is where I'll use as examples, but from watersheds all over the continental and as well as Puerto Rico and Alaska, so all over the United States. And so what happens what happens to the water balance when a forest is cut? This graph shows 6 different examples from these long-term studies. The time stamp on the bottom goes from about 1940 to almost 2010. And this shows how stream flow, or how the water balance, has changed as a result of cutting, and then changes in forest composition after cutting. Now, just to give you some idea of how to interpret this graph, anywhere where you see a 0 in the panels, that's no response. What that means is that the flow of the forest that was cut is identical to the flow of the forest that wasn't cut. When the value is above that line, okay, in this case we're talking about the blue bars and the black dots that are modeled to fit the bars, then stream flow from the cut forest is greater than the reference forest. When the blue bars are below the line, stream flow is less than what happened or what was going on in the reference uncut forest. So one of the first things we note is that stream flow increases, in some cases increases quite significantly when the forest is cut. And that's due to removing the leaf transpiration surface area and interception. And in some cases the increase can be as much as 400,000 gallons per acre. As the forest regrows, that amount of increases diminishes. And if we just focus on the upper two graphs, A and B, it essentially reaches the 0 point at about, in those forests, at about age 15 or so. Now, the upper two graphs also show that what happens over the long term is that forest flow or stream flow is now much lower than the reference forest than it was before. And the reason for that is that both of these represent an example where the hardwood forest was converted to a pine forest. So the pine forest is using more water than the hardwood forest. And remember, one of the things that I showed in the graph is that there's greater interception in the pine forest, and that's one of the reasons. And then the other reason is that there's greater transpiration that occurs in the milder climate here in the southern United States. So this is an example where you get an initial increase in flow. That flow diminishes quickly as the forest recovers to about what it was in the reference forest by about age 15, and then hereafter flow is about 20 or 25% lower than it is in the pine. So a shift in that water balance as a result of species composition changes. The other graphs show a variety of other things happening. One is a high elevation clear cut, that's C. A low elevation clear cut is D. Almost a different pattern, an increase in growth, but after the clear cut and the high elevation, its stream flow is actually lower than the reference, whereas the low elevation clear cut is still higher than the reference. Coppice forest, increase, cut again and increase, and then flow greater than the reference ever since. Old field succession kind of all over the place. What this shows, the take-home message here is a couple of things. One is you can greatly manipulate the water balance by manipulating the vegetation. In all cases, what's happening is we're changing the structure and the species composition in the forest. In some cases, that can be a fairly substantial change, as the example in the species conversion in the top two graphs. It's also interesting to note that in some cases we're now in the 40th or 50th year after cutting in these experiments, and except for perhaps the old field succession, none of the watersheds have returned from a water balance standpoint back to what they were prior to the disturbance, prior to the cutting. So here's a second question for you. Pop quiz number 2. In an earlier graph, I showed that transpiration was greater in most hardwoods at an individual tree basis than it was in pines. Remember, the pines and the hemlock had among the lowest individual tree transpiration rates than any of the hardwood trees. Why did, in the graph that I just showed you, why did converting from a hardwood forest to a pine forest result in a decrease in stream flow? And if you have some ideas or guesses, go ahead and type them up in the chat room, or just think about it and I'll show you the answer here on the next slide. Any guesses? All right. Well, the reason that's the case is that watersheds are made up of a compilation of individual species that create a stand, and that stand then had a greater interception because of the evergreen nature of the pine forest, and also had year-round transpiration in this moderate environment. So even though at the individual tree level, in the middle of the growing season, the pines have a much lower transpiration rate, at the annual level, on a well-stocked stand, it intercepted considerably more precipitation and then was able to transpire year-round with the moderate growing season typical of southern ecosystems. So what one of the take-home messages there is what happens at the individual tree isn't necessarily what's going to happen when you scale up to longer time frames and larger spatial scales. How does forest cutting impact water quality? The other thing, again, that we talked about, the value of the forested watershed is providing very high quality water. Well, what happens when you manage the forest in terms of water quality? Well, unfortunately, there's a long legacy of bad examples of how managed, or in this case, cut forests, I wouldn't even call them managed forests, have negative impacts on water quality. The upper right graph is you don't need to see the scale on it, but essentially, in some cases, a 10,000-fold increase in sediment or turbidity as a result of very poor logging practices. And in the old days, before we were enlightened and roads were built correctly, a lot of the skid trails and roads would go right up and down a watershed or be placed right alongside the stream without much clearer concern for the impacts on water quality. And as I noted earlier on, the most vulnerable and most important component of the watershed and the area where we'd expect most overland flow, erosion, and sedimentation comes from these roads and skid trails. So there is a legacy and a history of high sediment and poor water quality as a result of what were at the time very poor land management practices. Now we've come a long way in our knowledge about how to properly build forest roads and how to minimize the sediment movement from those roads when it occurs. And a lot of that has come from research and also on-the-ground experience. Instead of building roads up and down the watershed or right next to the stream, build them along the slope, pay close attention at road crossings, etc., the kinds of things I talked about before. And the bottom line is that when best management practices are in place, and in terms of sediment from forest road building or forest logging, those activities are compatible with protecting water quality and reducing sediment and turbidity in streams. It's not necessarily zero. This is an example from some of the studies at Coweta that showed that there are some vulnerable time periods where if you get a bad consequence here, in this case 2 major storms occurring right after road construction, you can still get some sediment pulses. But for the most part, those activities were very short-lived, and the rate of sediment production was essentially comparable to the reference. So forests can be managed in ways that protect water quality from a sediment standpoint. From a nutrient standpoint, there really is not much of an issue. This is a graph of a logged watershed at Coweta. The units here are microequivalents per liter. The drinking water standard is about 10 milligrams per liter. These are orders of magnitude lower than the drinking water standards. The lower solid line that you see there is what comes out of the reference watershed. Those are levels that are right at the detection limits because forest ecosystems essentially take up all the nitrogen that they can, especially in southern ecosystems. The fainter blue lines that you see are what happened on the logged watershed, and it's higher, and you'd expect it to be higher because you are disturbing the system and stimulating nutrient cycling processes. But and also there are some changes in species composition that may be altering nutrient cycling processes, but the levels are still very, very low and well below drinking water standards. So the summary of this is, in terms of effects on forest cutting on water quality, some of the key points that we know is that cutting alone does not cause erosion and stream sediment. It's how you get the logs out of the woods. So very careful protection of of roads, stream crossings, skid trails, etc. You can log without elevated sediment. And stream nutrient losses are very, very low and tightly controlled by that vegetation regrowth, which takes up any of that nitrogen or nutrients that are mobilized. What about fire and water quality? And quantity. Well, I'm going to talk primarily about quality, but also quantity. Prescribed fire is a common management tool in the South and increasingly used in other places for protection from wildfire or wildfire risk. One of the things that we've looked at in quite detail across the South is what happens in terms of water quality and quantity when you use fire. And what we find is that the response depends on fire severity. And responses to prescribed fire are usually quite minimal because severity is low. Responses to wildfire can be substantial, especially ones that have a high fire severity or burn severity, coupled with big storms that might occur immediately after a severe fire, and in areas that have steep slopes and rough, complex topography. And the types of factors then that influence watershed response is going to be how much of the forest floor you lose as a result of a severe fire, how much overstory mortality occurs, how fast the vegetation recovers, how that impacts infiltration rates. In some places in the United States, you can actually get some hydrophobic soils created as a result of fire, which lowers infiltration rates, and then some things that you can't control, like post-fire rainfall intensity and topography. This graph here essentially shows for some southern forest ecosystems, especially ones that had a very high mortality level, what happens to annual rainfall, or annual runoff, sorry. And the lower line shows the relationships between a control watershed and a burned watershed before the fire. So for 70 inches of runoff from one watershed, you got about 15 from the one that got burned. After severe fire, there was a significant increase in the amount of runoff from the burned watershed, and that was directly related to the fact that this was a watershed that had high mortality. About 50% of the trees were killed, and as a result, evapotranspiration was reduced and annual runoff increased. Now, this can happen and is typical in wildfire situations. Very rarely would this occur, if ever, in a prescribed fire situation. Same is kind of true with erosion and sedimentation. Where you have high severity, typical of wildfires, you get what occurs in the upper graph: high tree mortality, the complete loss of forest floor, and with post-fire storms, considerable amount of ash wash and surface erosion and rill formation. The lower part of the graph is more typical of a prescribed fire, where you still have live trees, you still have quite a bit of coarse woody debris, and as the lower right-hand panel shows, you might even still have understory vegetation and forest floor left. Now, you don't need a close-up view. Here's an example of a very large watershed that was severely altered as a result of forest cutting, in this case high intensity, not high severity, but a high intensity fire that consumed a lot of the downed material. But this experiment showed absolutely no movement of charcoal or sediment off-site. And why did that not occur? Well, really for three factors. One is this was a high intensity fire, but not a high severity fire, so the duff layer was maintained. As you can see in the picture, there's a lot of coarse woody debris that could act to trap any charcoal or sediment that flowed off of the site in high intense rainfall events. And this was also a watershed that had an intact riparian zone that didn't burn, and anything that would have flowed in small areas through this burned area would have been trapped and stored in that riparian zone. Same is true in terms of stream nitrate response to burning. Only in the most severe fires might you get a nitrate response, but for the most part, levels are incredibly low. Again, drinking water standards is 10 milligrams per liter. This is a bunch of different fires that have occurred, in this case in western North Carolina. Some of these are even wildfires. And in no case, while you might see a small increase in stream nitrogen, levels are always very low and well below drinking water standards. Okay, so I'm just going to summarize here and hit some key points, and then see if there's any questions after that. So my key points are as follows. Forests provide the cleanest and most regulated flows of fresh water among all land uses. Due to decades of research, this is a statement that is I'm quite confident in, and as the National Research Council said, it's settled science. That relationship is determined by the climate, vegetation, soil interaction, which determines the overall site water balance and water quality. That can be manipulated to either increase or decrease flow as a result of disturbance or management choices, which either change age class or structure or change species. There is enough in that relationship that flow can be either increased or decreased depending upon management activities. Riparian zones are the critical watershed feature. They're the place where sediment and nutrients are trapped as it flows from the upland to the stream surface water zone. And having a healthy functioning riparian zone whose width can be determined by a variety of factors is a critical part for maintaining water quality. Forests can be managed in ways that protect water quality, paying attention to keeping the forest floor intact and ensuring infiltration and having a rapid vegetation regrowth is some of the key practices that can be implemented in order to do that. Okay, so that's the material that I wanted to cover in my hour. Be happy to answer any questions through whatever process is used here to do that, Bill.
Great. Thank you, Jim. That was a fantastic overview. And just a reminder, folks, this will be archived too, so that if there's any information that you feel you need to go back over, we'll have it up online in the next few weeks or so. Do we have a question? Rebecca has her hand up. Rebecca, let's see. I'll give you audio permission, or if you'd like, you can go ahead and chat your question in. You should have audio permission right now. I guess I'm not sure if she has a question or not, Jim.
Okay.
In the meantime, while we are going through this, I'm going to push out a URL that will allow you to take your quiz and obtain your credit. Hopefully it's redirecting as we speak here. I have also put it in the chat box so you can link to that, but you can see here, you can go ahead and put in your email address and you should have no trouble moving forward from there. Okay, it looks like Jim, you did a marvelous job here. This is nice when we don't have a lot of questions. Issues come up, so let me know if anybody has issues. Moving on from the quiz, you can go again, take your quiz and receive your credits. We are just right at the hour mark. We told folks we would take no more than an hour of their time. As Dr. Vose mentioned, we have 2 more webinars in this series. We've got the next one scheduled for July, and that will be July 9th at 2 p.m. and that one is Influence of Forest Cover Loss and Land Use Change on Water Quantity and Quality. Again, that will be July 11th, or July 9th, excuse me. And then our final one will be August 6th, and that will be application of forestry best management practices for water quality protection. So this is our summer water series designed to keep you cool out there. So again, Jim, thank you very much. Did a marvelous job. Everyone please join me in thanking Jim, and everybody have a great day. Take care now.
All right. Thank you.
Bye-bye.
Bye-bye.